Good morning, students. Palkana Namaskar. So, in the last class, we were discussing about vibration of air column in a pipe closed at one end and in a pipe open at both the ends. In a pipe open at both the ends. While discussing the vibration of air column in a pipe open at both the ends or in closed pipe, the boundary condition suggests that always node is formed at closed end and antinode is formed at open end. Antinode does not form exactly at the open end but slightly above it. So this is called end correction E. End correction E is equal to 0.3 times of D. The corrected length for closed pipe L is equal to if small l be the length of air column, then capital L, that is corrected length, is equal to small l plus E, which is equal to small l plus 0.3D. But in the case of a pipe open at both the ends, a boundary condition suggests that always antinode is formed exactly at open end and node is in between. In this case also, if small l be the length of air column, then the corrected length for open pipe capital L is equal to small l plus 2e, because end correction is applied from both the sides in upward and downward direction, both the sides. We have proved that, in the last class we have proved that the frequency produced in a vibration of air column in a closed pipe are, if n is fundamental frequency, its higher frequency is 3n, next higher frequency is 5n, next higher frequency is 7n. So, frequency produced in the vibration of air column are odd multiples of fundamental frequency, or odd rules are odd multiples of fundamental frequency. Or in other words, even harmonics are not present in the vibration of air column in a closed pipe. But in the case of open pipe, we have proved that if n is fundamental frequency, 2n is next harmonic, 3n is next frequency, 4n is next frequency, like this. So, from this we conclude that the frequency produced in vibration of air column in a pipe open at both ends are integral multiple of fundamental frequency, or all harmonics are present as overtone in vibration of air column in a pipe open at both ends. So if you concentrate on the end correction E or corrected length L, in the case of closed pipe, your end correction is applied for only one side. End correction is applied for only one side. But in the case of open pipe, end correction, antinode, node, it is applied on both the sides. Reynolds has proved that end correction E is equal to 0.3D. where D is inner diameter of tube. It is an empirical formula. If we have fundamental frequency in the case of closed pipe is given by n is equal to V upon 4L, or which is equal to V upon 4 L plus small l plus E. In this case, n is equal to V upon 2 L plus 2E. If there is error in measurement of small e, as it appears in the denominator, the value of frequency, there will be large change in frequency. The value of frequency will be large change. Or in other words, small change in small e will produce large change in L. In this case also same thing. Therefore, while measuring the end correction E, we have to take more precautions. Is there any way to eliminate E without measuring diameter? Can we eliminate D, or we can eliminate E? Yes. That's what we are going to discuss today. The next article is practical determination of end correction. Practical determination of end correction. Of end correction. Let us determine end correction practically in closed pipe and in open pipe. For closed pipe, fundamental frequency is given by N is equal to V upon 4L, where L is what? Corrected length, or V is equal to 4N L small l plus E. Velocity of sound for a given medium, is constant. That means if we change the frequency, there will be change in length of air column. And the product always remains constant. We can say that V is equal to 4N L1 is equal to 4N2 L2, which is equal to what? Equal to constant. As fundamental frequency of vibration of air column for a closed pipe is given by N is equal to V upon 4L. For L is their corrected length, or V is equal to 4N into L plus E. Where L is the what? Length of pipe or length of air column. If the frequency changes, the length of air column changes, or velocity of sound for a given medium remains constant. Therefore, we can write V is equal to 4NL, N1 N2 N is equal to constant. By simplifying, we get N1 L1 is equal to N2 L2. N1 L1 is equal to N2 L2. Register. Or N1, L1 is what? Small l1 plus E, because for closed pipe correction is applied for only one side. N2 L2 plus E, N1 L1 plus N1 E equal to N2 L2 plus N2 E. Again simplify, let us take E quantity on other side and N1 L1 on other side. N1 L1 minus N2 L2 is equal to N2 E minus N1 E. Or if we simplify, we get E is equal to N1 L1 minus N2 L2 equal to N2 minus N1. N2 minus N1, or E is equal to, if you take common, if you take minus common, what we get? N2L2 minus N1L1 divided by N1 minus N2. N1 minus N2. So by this formula, by this expression, we can determine the end correction without measuring the diameter of the tube. End correction can be determined by measuring the diameter of the tube. But in this case, without measuring diameter, we can determine the end correction, or we have eliminated the diameter of the tube. So for the closed pipe, end correction is given E is equal to N2L2 minus N1 minus N2. For open pipe, similarly, for open pipe, the fundamental frequency of vibration is given by Vn is equal to V upon 2 L plus 2E. L plus 2E. Because 2 appears because end correction is applied on both the sides. Or we can write V equal to velocity of sound, V equal to 2 N L plus 2E. As in the same case, same conclusions we can draw. If velocity of sound remains constant for the given medium, that means if the frequency changes, length, vibrating length or length of air column changes. That means we can write V is equal to 2N1 L1, which is equal to 2N2 L2, which is equal to constant. Or if you simplify, we get 2N1 L1 equal to 2N2 L2. N1 L1 is equal to N2 L2. Further, N1 L1 is what? L1 plus 2E, N2 L2 plus 2E. Again simplify, N1 L1 plus 2N1 E1 E, N2 L2 plus 2 N2 E. We take left hand side N1 L1 minus N2 L2, this term, and E term to right hand side, 2 N2 E minus 2 N1 E. Finally we get E is equal to what? E is common, N1 L1 minus N2 L2 divided by 2 is common again, N what? N2 minus N1. Or we can write in the form of N2 minus N2 L2 minus N1 L1 equal to twice of N1 minus N2. So by this expression we can eliminate end correction, or we can determine end correction practically without measuring the diameter of the tube. In the case of closed pipe, end correction can be given or determined by the expression N2 L2 minus N1 minus N1 minus N2. For the open pipe, E can be determined, E is equal to N2 L2 minus N1 over 2 N1 minus N2. So by this way, We conclude the article determination of end correction, practical determination of end correction. So let us discuss next article, that is vibration produced in a string. Vibration produced in a string. Let us consider a string stretched between two fixed endpoints. That means a tension is produced in the string, say T with a tension in the string. Let L be the length of string and small m be the mass per unit length. Mass per unit length. Or it is also called linear density. It is also called linear density. If such a string is plucked at its center and released, transverse views are set up in the string. These transverse views reflect from the fixed end points. And transverse views reflect from fixed end points. If the fixed point is denser medium, if it is the medium is denser, and crest is instead reflected as trough is reflected as crest. As trough is there, it is reflected as crest. Incident view and reflected view. Incident view is denoted by a bold line, and reflected view is drawn by a dotted line. Incident view and reflected view interfere each other. Stationary views are set up in the string. Such that always, due to boundary condition, always node is formed at the fixed point, antinode is in between. The velocity of transverse view in the stretched string is given by V is equal to under root T by M. Once again I repeat. Let us consider a string of length small l is stretched between two fixed endpoints. That means we have produced the tension in the string. Let T be the tension in the string. Let small m be the mass per unit length or linear density of the string. Now, this is what we have considered. If the string is stretched bit, if the string is plugged at its center and released, string starts to vibrate. Due to vibration, transverse waves are set up. These transverse waves reflect from the end points by change in phase. The change in phase. The reflected wave and incident wave interfere each other, and stationary waves are set up in the string. The boundary condition or suggests that always node is formed at fixed point, antinode is in between. The velocity of transverse wave in stretched string is given as V is equal to under root T by M. This you have to remember. Velocity of transverse wave is given V is equal to under root T by M. So string can vibrate in different ways. In this case, two loops are formed. Same string can be made to vibrate by forming a single loop like this. If single loop is formed, the frequency is different. Two loops are formed, frequency different. If three loops are formed like this, say, roughly I have drawn, the frequency of vibration will be different. For the same length of string, a string can vibrate in different ways. By forming a single loop, by forming two loops, by forming three loops. That means string can vibrate in different ways. The different ways of vibration of stretched string is called modes of vibration. What we are discussing? Vibration produced in a string. How the vibrations are produced? Transverse waves are produced, and these transverse interfere each other, stationary waves are produced. So string can vibrate in different ways, and the different ways of vibration is called modes of vibration of stretched string. How they vibrate, what would be the frequency, we have to discuss. What would be the relation between the frequencies, that what we are going to discuss. Okay. Modes of vibration. Modes of vibration. Of string. Same article, a different article is not the same article, sub-article say. Modes of vibration of string. Let us say consider, so we have different, for same length, for same tension. First case, second case, third case. Okay. The length of string is kept constant. For in all the cases, length of string and tension of the string is kept constant. For the same length and for the same tension, a string can vibrate in different ways. As shown in figure A, figure B, figure C. For the same length, one loop is formed, that means antinode, node and node. So let small l be the length of string in this case. Node, antinode, node, antinode, node. Length of string small l. Node, antinode, antinode, antinode. N, node, say node, node. Length of string small l. In this case, the frequency be say n and wavelength be lambda. In this case, the frequency be n1 and wavelength be lambda 1. In this case, frequency be n2, wavelength be lambda 2. From figure, what do we observe? A string can vibrate in different ways or different frequencies. One loop is formed, two loop is formed, three loops are formed. The frequencies are different, n lambda, n1 lambda 1, n2 lambda 2. In the simplest mode of vibration, the simplest mode of vibration of string or stretched string is as shown in figure A. It consists of two nodes and one antinode. Let n be the frequency of vibration and lambda be the wavelength of the wave. So we know that V velocity is equal to n lambda or n is equal to V upon lambda. But from figure, length of string small l is equal to distance between two successive nodes is lambda by 2. And we have proved that or discussed that velocity of waves in stretched string is V is equal to under root T by M. Therefore, we get n is equal to what? V is equal to what? 1 upon lambda under root T by M. But lambda is equal to 2L. or n is equal to 1 upon 2l under root T by m. The frequency of vibration, we have determined the expression for frequency of vibration in a stretched string. It is the simplest or it is a fundamental. Therefore, the frequency of vibration is called fundamental frequency. Or it is also called harmonic, first harmonic. The frequency of vibration in the simplest mode is called fundamental frequency or is called first harmonic. The second mode of vibration is as shown in figure B. It consists of two loops. It consists of two loops or it consists of two nodes, three nodes and two antinodes. Let in this case n1 comma lambda 1 be the frequency and wavelength of the wave in the second mode. So from this expression we get n1 is equal to v upon lambda 1. n1 is equal to, as we know already, lambda 1 under root T by m. Velocity of transverse stretched string is given by v is equal to under root T by m. But we don't know lambda. Lambda can be determined in the form of L. As we know we can measure the length of string. So from figure B, length of string is equal to distance between two successive nodes is lambda by 2 plus lambda by 2. That means lambda 1 by 2 plus lambda 1 by 2, because in this case we have considered wavelength as lambda 1 or small l is equal to lambda 1. Therefore, n1 is equal to 1 upon L under root T by m. If we compare these two equations, we get n1 is equal to 2n. If you compare the frequency in second mode, it is twice the frequency of fundamental mode. And it is also next higher frequency than the fundamental mode. If you compare or if you observe, frequency of vibration in second mode is twice the frequency of fundamental frequency. Also, it is next higher frequency than the fundamental. Therefore, it is called first overtone. First overtone, and as it is twice, it is called second harmonic. Second harmonic. Similarly, the next mode of vibration is as shown in figure C. It consists of three loops, or we can say four nodes, 1, 2, 3, 4 nodes and 3 antinodes. In this case, say n2 with the frequency, lambda 2 with the wavelength, or n2 comma lambda 2 with the frequency and wavelength of the wave. Similarly, n2 is equal to v upon lambda 2, or n2 is equal to 1 upon lambda 2 under root T by m. It is no need to state once again. As we know, v is equal to under root T by m. But from figure C, length of string small l Distance between two successive nodes is lambda by 2 plus lambda by 2. That is lambda 2 by 2 plus lambda 2 by 2 plus lambda 2 by 2. Or which is L is equal to half plus half is 1, 1 plus half is 1.5, or 3 by 2, 3 by 2 lambda 2. Or lambda 2 is equal to 2L by 3. Substituting our equation, we get N2 is equal to, or lambda 2 is equal to 2L by 3. N2 is equal to 1 upon lambda 2 is equal to what? 2L by 3. 3 upon 1 upon 2L under root T by M. If you compare this equation to this fundamental frequency, we get N2 is equal to 3N. Or the frequency of vibration in third mode is higher than the first overtone. Next higher than the first overtone, hence it is called second overtone. Next higher frequency than the first overtone, so it is called second overtone, and it is multiple of 3 of fundamental frequency, or thrice of fundamental frequency, hence it is called third harmonic. So frequency of vibration in first mode is called fundamental or first harmonic, which is given by this. Frequency of vibration in second mode is given by N1 is equal to 1 upon L T upon N. N1 2N, it is called first order or second harmonic. In third mode, it is N2 is equal to 3 by 2L under root T by M, or N2 is 3M, which is second overtone or third harmonic. So generally, a thin equation often we can generally we can state the vibration frequency produced in the vibration of stretched string. If N is the fundamental frequency, N1 is 2N, next frequency is 2N, next higher frequency is 3N, next higher frequency will be 4N, next higher frequency will be 5N, dash, 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 dash. That is frequency produced in the vibration of stretched string are given by N, 2N, 3N, 4N, 5N. N, 2N, 3N, 4N, 5N, dash, dash, dash. So, what do we conclude? We conclude that frequency produced are integral multiple of fundamental frequency. If N is the fundamental frequency, next frequency are 2N, 3N, 4N, 5N. So, integral multiple of fundamental frequency. And second one is overtones, first overtone, second overtone. All overtones are produced, all harmonics are produced. Once again, all harmonics are present as overtone. All harmonics, 2N, 3N, 4N, 5N, all harmonics are present as overtone. So, by this way, we complete the article vibration produced in stretched string. What you have to remember? You have to remember that frequency produced in vibration of stretched string are first integral multiple of fundamental frequency, second overtone produced are integral multiple of fundamental frequency, or third harmonics are present as overtone. Let us see how much is the time. 40 minutes. Next article is laws of vibrating string. Fundamental frequency of vibrating string is given by n is equal to 1 upon 2L under root T by M, where T is the tension in the string, M is so-called linear density, or it is also called mass per unit length. Where L is the length of string. So there are three laws governing vibrating strings. The first law is law of length. It is not called first law, it is called law of length. Three laws are formed. Three laws will form. In the given formula n, we have three quantities. P is constant quantity, L is changing, T is changing, M is changing. Say. Out of three, two are kept constant. Only one will be variable. Due to that, the frequency will also changing. If tension and mass per unit length are constant, what do we get? N is what? Some equal to some constant divided upon L. N is proportional to 1 upon L. This is what the law. Law of length of vibrating string states that, important to note, this law is only stated for the fundamental frequency. It is related only for the fundamental frequency, not for overtone, not for harmonics. Not for harmonics. So law of length states that if tension and mass per unit length are kept a constant, the fundamental frequency of string is inversely proportional to length of string when tension and mass per unit length are kept constant. When tension and mass per unit length are kept constant. Okay. Or we can generalize n equal to some constant divided by L, or NL is equal to constant. NL is equal to constant means N1 L1 is equal to N2 L2 is equal to N3 L3 equal to dash 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 is equal to constant. That means if the length is changed, frequency changes, the product always remains constant. That's what the law of length. Second law, that is law of tension. Law of tension states that law of tension. Sorry, I have read the fundamental frequency is given 1 upon 2L under root T by M. In this case, if length and mass are kept constant, the whole quantity becomes constant, or what do we get? N is equal to some constant under root T, or M proportional to root T. When length and M are constant. Hence we can state that the law of tension states that the fundamental frequency, remember once again I repeat, these laws are related only for fundamental frequency. Fundamental frequency of vibration of stress resisting is directly proportional to square root of tension when length and mass per unit are kept constants. Or in other words, from this equation we can write N upon root T equal to constant, or say N1 upon root T1 equal to N2 upon root T2 equal to dash dash equal to constant. These formulas, these equations, these expressions are fruitful to determine for solving the problems, numerical problems. They are very fruitful to solve the problems, numerical problems. Third law, or you can say law of mass. In this equation, if length and T are constant, 2 is also constant, then N is equal to 1 upon root M into constant, or N is proportional to 1 upon root M. When L and M are constant. How do we state? Law of mass states that the fundamental frequency of vibration of stress resisting is directly inversely proportional to square root of mass per unit length when length and tension are kept constant. And length and tension are kept constant. Or we can, you know that mass equal to what? Mass per unit length. Let capital M be the mass of body, let small l be the length. And mass for small m is equal to, mass is equal to density into volume. Volume into density divided by L, or small m, volume of uniform wire, cross sectional area, pi r square, into length divided by L into density rho. L get cancels, or small m equal to pi r square rho. In this equation we can substitute as n is proportional to 1 upon root pi r square rho, or n is proportional to if you remove pi outside, constant 1 upon rho r. If you take r outside, the square root under root of rho. If you simplify, so law of mass can also, first statement for law of mass is fundamental frequency is inversely proportional to square root of linear density when length and tension are kept a constant. Second statement will be the fundamental frequency of vibration of stress string is first inversely proportional to radius, second it is inversely proportional to square root of density of the wire when length and tension are kept constant. In short, we state once again, law of length states that fundamental frequency of vibration of stress string is inversely proportional to length of string and tension and mass unit length are kept constant. Second statement, law of tension states that fundamental frequency of stress string is directly proportional to square root of tension when length and linear density are kept constant. These formulas for solving the numerical problems. Law of mass. Fundamental frequency of vibration of stress string is inversely proportional to linear density m when length and tension are kept constant. If we solve for the density and radius of the wire, we arrive the law by this way. Fundamental frequency is inversely proportional to first statement is radius of wire and second is inversely proportional to square root of density of wire. So we will stop here. Let us continue tomorrow. Thank you.